The Lecture 17 demos. In the first one, if we walked along with a bicycle wheel without spinning and with spinning, well, if we were walking at a certain speed v, then in fact the center of mass velocity for both is just v. And one way to think about that is that actually the total momentum is just the total mass times the velocity of the center mass. It's sort of a squish theorem. And so what you can think about is that relative to the center of this thing and that reference frame, all these other parts are relative to it are canceling out. This is going forward, this is going backwards, and so forth, all around in the symmetric case. And so it is that it doesn't matter if it's spinning like mad. If we knew the center's speed v, we know the center of mass velocity. In a similar fashion, when we threw a bat through the air, we have this wonderful overall squish theorem that the net external force, all the internal cancel, the net external forces will be just the total mass times the acceleration of the center of mass, no matter whether it's spinning or not. And we have only gravity. If there's only gravity here, ignore air drag, then that center of mass must just simply follow what a point particle with mass m would be, a squish theorem. And sure enough, we saw that tape, we followed the tape along, and it was just a nice smooth guy, even though the bat might be spinning. In the last demo, we ran a car along a board, that's free itself to rotate on a frictionless support. So if I have a car here, I have a board here, and they have the same mass, then the center of the board is here, then and the car is here, and they have the same mass. And remember, you can just imagine a squish to a point. Then the center mass is halfway between them. Afterwards, we know that the car has gone to the other end of the board. And sure enough, then that center of mass in that configuration is there. So we have to put that center mass and just draw it right below so that the center of mass is exactly the same place. And sure enough, that's roughly what we saw in the demo. By the way, it's kind of cute. You could almost imagine that this board could be replaced by a mass that was equal to that mass. And it would be like Ricardo and Carmelita switching places. If they were having the same mass, the center of mass would stay put. And I'd have Ricardo, Carmelita here, and then Ricardo here and Carmelita here. And the positioning of the boards, follow suit. The demos for Lecture 19. We have our loop-the-loop problem, where we have a marble and we let it roll down. And the question is, how can we make it go all the way around the loop-the-loop? Well, it's not just energy. It's true, let me just draw a little line here, that if I started here, then just by energy, I would know I'd get to that same height, at the other end if I were just going up and down a hill, something like that. But here, what happens is before it gets to the top of this, it'll fall off the track if it's going too slowly. Gravity will pull it off of the track. So it isn't possible to make it get to the top from here. You're going to have to go up here some distance. And to analyze how far up you need to go, you need both energy conservation, and you got to use the second law radially, where you can ask, okay, at what point does the normal force inward holding it in the track just vanish? That's the analysis you need to see if you get to the top, and not just energy conservation. For the steel marble, nudged at the top, of the cylinder, and eventually it gets going fast enough that it flies off. It's the same story, where it's not just an energy thing. I've got to ask the question, at what point does the contact force vanish. You know, it's holding things up and then it gets less and less and then vanishes right when it leaves. It loses contact. So I need both energy conservation, comparing the two places, and my second law radially where I can put in that constraint that the normal force just vanishes. Finally, our spool thing, which was always a surprise. If I have my spool and I'm pulling on the top, everyone sort of is comfortable with the fact that this will just rotate like this and move to the right. Well, here is a little surprise. If I'm pulling from below, it also rotates around the contact point, which is instantaneously at rest. That's my good rotational thing. That's my net torque. You know, no torque's due to the contact force at that point. The only torque would be due to this force, and that's above such as to make a clockwise rotation around this and moves to the right. All cases move to the right, because when you jerk on it, then you know you break free from the floor, and it's like, you know, sliding on ice or something. You just got a net force to the right, and it pushes it it pulls it to the right. The last demos from lecture 20 and lecture 23. By the way, delete this one. We didn't actually get to this. We'll do it in the second or the third cycle. In lecture 20, it was our good old monkey bananas demo. If I have a monkey hanging on one side and bananas on the other, and they have the same mass, you know, they'd just be balancing each other. But the monkey now can, you know, by using his muscles, climb up this thing, you know, giving himself an acceleration, and he would have, you know, the tension minus the tension that he generates by pulling hard minus mg equals ma, and you find what the acceleration is for that. That's the identical equation for the bananas, upward. Same mass, you know, the same tension because I don't have any mass on my pulley, and therefore the same acceleration. So they go up together. By the way, if they were just hanging there, the monkey could just kind of let himself slide down, keeping the tension the same because the acceleration is zero, and the monkey and the bananas wouldn't move then. You may remember that from the last part of the demo. This could slide down at constant speed, and this one would stay put. Finally, we've got a strip of paper. We pull it with, say, speed u. We have our little motorized car. We want to get straight across. We want to get to this. Say, if I start here, you know, imagine on you know, the board and outside, the floor outside, and we want to get to the same place, you know, directly across on the floor. I know I have to aim it like this. How? What should this angle be? The angle should be such that my component of my velocity v, of my motorized car, you know, relative to the strip of paper, the component horizontally should be equal and opposite to the velocity of the strip. Because then if that cancels, then the only thing left relative to that reference frame is something going straight across. And you can then calculate sine theta as u over v if you wanted the angle. So if u were really big, you know, u is really big, I can't ever cancel that. You know, and I certainly can't cancel it so that I go straight across. In fact, if u is greater than v.